and welcome to our virtual Lunch and Learn. Today we're talking about Introduction to Integrated Motion Studio 5000. My name is Rachel Green. I'm the Digital Communications Specialist here at McNaughton-McKay Electric Company. And presenting for us today is Andrew Mazzola, Systems Engineer out of our Madison Heights, Michigan location. Out in the comment section, ready to answer your questions, is Steve McDonald, Systems Engineer also out of Madison Heights. We will also have a Q&A portion at the end for Andrew to answer your questions in more depth. We'll be getting started shortly, but we'd like to allow a few minutes for attendees to join us. As you come in, let us know where you're tuning in from in the comments section. You can view recordings of previous virtual Lunch and Learns on our YouTube channel under the Virtual Lunch and Learn playlist, and we cover a new topic every Wednesday at noon, so be sure to join us on your lunch break. For anyone just joining us, welcome to our virtual Lunch and Learn Introduction to Integrated Motion Studio 5000. Let us know where you're joining us from in the comment section. Our specialist, Steve McDonald, is ready to respond to your questions in the comments as we go along, and we will also have that Q&A segment at the end of Andrew's presentation. If you'd like to reach out afterwards, or if you have further questions for Andrew, you can always send us an email at macandmaclive@macandmac.com. Be sure to let us know which session you attended so we can direct your questions to Andrew. We will also have that email address on the screen for you at the end of the presentation as well. And it looks like we have a number of viewers with us. So Andrew, I'm going to pass it over to you now.
Okay, thank you, Rachel. Like Rachel mentioned, my name is Andrew Mazzola. I'm a systems engineer in the Drives and Motion Mechanical group out of Madison Heights for McNaughton-McKay. And today I'm going to give us a little introduction to integrated motion. And so for an overview of this presentation, I'm going to show us how to create a module definition for your drive. Also that an Axis configuration, how to set that up in Studio 5000. We're going to look at setting up trending so we can look at some graphs of what the Axis is doing, some of the data coming back from the drive. And I'm also going to give an introduction and overview of some of the Axis commands, some of the basic ones, just to give you an idea of how to get started moving the Axis. And so the first thing you're going to do is create a new project in Studio 5000 and select your controller, which you'll see on the right. Once you've done that, you're going to want to make sure that you've configured the date and time settings for your controller and any of your Ethernet scanners to enable time synchronization. So you'll see on the right, if you go in your controller properties in the date and time tab, make sure enable time synchronization is ticked. And this is also known as IEEE 1588. And you're going to need to have this enabled in order to use CIP motion in your controller so that the devices can pass that type of traffic to your drives. So once that's done, you're going to go into your the bottom of your controller organizer and look for the IO configuration folder. Find an Ethernet node that the drives are connected to, and right-click on that and select New Module. You'll see the Select Module Type window appear, and from here you'll select your part number of your drive. So in this case, just as an example, I've selected 2198H008-ERS2, and this is a Kinetics 5500 servo drive, and this one in particular has network-based safety, so it works with a Guard Logix controller. And once you've done that, you'll see that new module window appear. You're going to assign a name. So in this case, just as an example, I've called it turntable drive, and you're going to need to assign an IP address, and then you're going to want to go into the module definition, click on that change button, and make sure your connection type is set up properly. So if you want network-based safety to be enabled between the drive and the PLC, you're going to leave the connection type as motion and safety. But if you want to do hardwired-based safety, such as if you had a Kinetics 5700 or an ERS-style drive, you would make sure that connection is just set to motion only, and then you would do the safe torque off in a hardwired fashion. If that connection type is set to motion and safety and you try to do hardwired network-based safety, you'll receive a fault. So next we're going to go to the Power tab in this same window, And make sure that your bus sharing is set up properly, the way that you are sharing AC or DC between your drives. Make sure your voltage is set up properly here. That's very important. And then also the input voltage to the drive. And then also make sure that your shunt regulator is set up here. So if you have an external dB resistor, you're going to tick that external radio button right there at the bottom, and you're going to add the part number in the external shunt field right there. And then press OK. And so now we're done configuring our drive module for a basic application. So next, the new project, you're going to have to create a new motion group. And so right-click on the motion groups folder in the controller organizer. And then you're going to give that motion group a name. And then press OK. You can just use the default properties here, typically. And then once you've done that, you'll see a new motion group folder under the motion groups folder. And it'll have the name that you assigned it. Well, anyways, right-click on that motion group folder and select New Axis. And then the Axis type will be Axis CIP drive. And this is the type of Axis tag that we're going to use for all the modern CIP-based servo drives, such as the Kinetics 5500, 5700, and PowerFlex 755 drives that are using CIP. And once you've selected Axis CIP drive, you'll see this new tag window up here. And you're going to give that a name. So in my example, I just called it Rotary Axis. And then you can leave everything as default and press OK. So once you've done that, you'll be presented with the Axis Properties window. You can also reach this by right-clicking on the Axis name that we just created and clicking on Properties if you want to open up this window again. But it'll open up immediately once you create the Axis. And on this General tab, make sure that you associate the module that we created previously with this Axis. So that module that I created before called Turntable Drive, I'm going to select that in the Module field dropdown under Associated Module. I'm also going to make sure that my group is assigned to this Axis. So in the motion group field, you'll see it says it's set to motion group. Once those two objects are assigned to this Axis, then we can click on Apply. And then you're going to want to click on the Motor tab on the left. And we're going to add our particular motor that we have to this Axis configuration. So in this example, I've selected my data source as catalog number. And then I've clicked on the Change Catalog button right there. And I've selected a VPL B1003F-P just for this example. And then I'm going to click on OK. Once you do that, you'll see all these fields automatically populate because the software already knows the data for this motor. So we don't have anything else to do on this screen. Click on the Motor Feedback tab. You'll see that that also all populated automatically. If you have an induction motor that you're using, particular drives do support that, then you'll have to add these two pieces of data, or all this data, really manually. But for a Rockwell servo motor, it's all set automatically by the software once you set the catalog number. Once you've done that, we're going to go to the scaling. So click on the scaling tab and you'll be presented with a screen like this. And this is an example for a rotary, and I also have a linear that we're going to touch on in a minute. But if you do have a rotary axis, for the load type at the top, you're going to want to select rotary transmission. And then, for example, if you had a 50-to-1 gear reducer that was attached to the motor, maybe between the motor and the cam table, then you're going to put the ratio of that gearbox in the transmission field. And so I've selected 50-to-1 for a 50-to-1 gear reduction there, just as an example. And then I like to do my scaling in terms of degrees. And so for my units, I just typed in the string degrees, and then I've set my scaling for that units, the engineering units, to 360. And the way that reads is 360 degrees per one load rev. And then I wanted this to have unwind. I wanted this axis to, these counts to automatically roll over when we get to 360 back to 0. And so I set my travel mode to cyclic, and I set my unwind to 360 degrees per one cycle. And that's what you'll typically see in a rotary axis scaling configuration. Now, if you had a linear axis, you're going to want to set your load type to linear actuator at the top. And let's say you had a 7-to-1 gear reduction between your motor and your ball screw or belt drive. You're going to have a 7-to-1 ratio right there in your transmission field, or and that corresponds to your gear reducer. For your actuator selection for your type, if you have a ball screw, select screw. If you have a belt and pulley, select belt and pulley. And you're going to fill in the lead or the diameter in terms of millimeters per rev for the lead, or in terms of millimeters for the diameter of the pulley right there. And that's pretty straightforward. Now for your scaling, for my units, I like to use millimeters. And that would read 1 millimeters per 1 load millimeter. And then for my travel mode, I've selected limited, just for this example, in my range of 1,000. And what this means is that when I'm giving Axis commands, it'll only respond to Axis commands that are moving between 0 and 1,000 millimeters with respect to home. So if you'd like an unlimited travel range, you can set it for unlimited as well. And if you'd like to have soft travel limits, you can tick that box at the very bottom right there, set up maximum and positive and maximum negative travel limits. And then I'm going to just briefly touch on configuring adaptive tuning for this axis. So in about 90% of applications, adaptive tuning will work really well so that you won't have to auto-tune or manually tune the axis. What this does is it allows the axis to dynamically and automatically all the time monitor the load of the axis and then configure some of its tuning parameters on the fly constantly. And this seems to work really well, like I said, for 90% of applications. So to enable this, first you're going to go to the Auto Tune tab, select a custom application type, and then uncheck the torque low pass filter. And this is starting with the default configuration, mind you. So it's going to look something like this. Click on Apply. Now select the Load tab. Make sure that Use Load Ratio is checked, and then set your load ratio to 0. And click on Apply. Go to the Compliance tab. For adaptive tuning configuration, just pull down that field and select Tracking Notch, and click on Apply. And then in the Observer tab, you're going to, for the configuration, select Load Observer with Velocity Estimate. And with these two features enabled, Load Observer and Tracking Notch Filter, like I said, the axis will dynamically tune itself to the load, and it will also look for resonant frequencies and try to tune those out, and that specifically is what the Tracking Notch Filter does. All right, and then another question that I get asked a lot is some of the tags for the axis sometimes won't update, but you'll see them as 0, like your axis name dot output current tag might be 0 in your PLC, or even though the axis is running, or your position feedback is always showing as 0. If you see that, you're going to have to go to the Cyclic Parameters tab of your axis properties and just tick the boxes corresponding to the tags that you want to be written from the drive to the PLC. Any of these tags that you see in here, if they're unchecked, they will always remain 0 value in the PLC, and that's just to save on the bandwidth of the communications that's going between the drive and the PLC. They're not all enabled by default. Another question that we run into a lot for these types of servo axes, for hardware overtravels, by default, the hardware overtravel exception or action is set to disable. And what that means is that when you reach the hardware overtravel switch, the drive disables and the motor brake sets, and you have a hardware overtravel fault. The problem with leaving it as disable is that once you have that hardware overtravel fault and the axis turns off, you cannot MSO or turn on the axis until that hardware overtravel switch is unmade. Problem there is your motor brake is set, so you're really stuck. And you can't jog off of it. So what you typically would do is set this exception for the hardware overtravels to stop planner. That way, when you reach the hardware overtravel switch, all of the current motion will stop, but the drive will be left running, and so you'll still be able to jog the axis in the opposite direction. Even though you have, for example, a hardware overtravel positive fault, as long as the drive is running, you can still jog it in the negative direction. And that'll be that way, it's just a lot easier to recover from that type of a fault with stop planner. So next, I'm just going to touch on creating a trend. And so in your controller organizer on your left, look for a folder called Assets, and then inside of that, look for a folder called Trends. Right-click on that and select New Trend. You'll be presented with a window where you can name this trend. So just enter in a name and then click on Next. These are some of the typical axis tags that we're going to add to a trend to monitor the health of the axis. So it'll be like axis name dot output current dot torque reference, actual position, command position, actual velocity, and command velocity. So the output current is going to tell us how much current the drive is outputting it, or like how hard it's working. If you go into a hard stop, for example, drive into a hard stop, you'll see that output current spike really high. Torque reference is telling us the drive's torque that it's trying to meet and trying to produce in the motor. The actual and command position are quite self-explanatory. The actual position is the feedback coming back from the motor as far as its position. Command position is where the axis is trying to go at this moment in time. And then same goes for the actual and command velocity, but in terms of velocity. And the difference between actual and command position is the position error. And the difference between the actual and command velocity is the velocity error. And you'll notice that as the error builds, typically those loops will try harder to close out that error, depending on your tuning, your gains. But in any case, once we have these tags added to our trend configuration, we're just going to go ahead and click on Finish. And then you'll be presented with this the trend window. I really don't like the default chart properties, so we're going to go ahead and I'm going to show you how to change them. Go ahead and right-click on that background of the chart. Select Chart Properties. In the X-axis tab, the default time span of 2 seconds is really too short, so we're going to change that time span to 20 seconds. And then for the Y-axis, we're going to select Preset Min and Max Settings for the Pens tab. What that'll let us do is then we can go to the Pens tab, and then you'll see that each of these tags has a min and max value that we can set. And you're just going to set those based on kind of an estimate of where you think the ranges for that particular value lie. For your application, it might be different, but that way you're scaling the y-axis for that individual pen. Once you're done with that, click on Apply and OK, and then you'll be presented with the trend window. Just click on the Run button in the upper left, and you'll see the pen start to draw. And then as you move the axis and as those tags change, you'll see the pens draw. And I should mention, you can also trend any tag in the controller. So if there's a particular logic bit you wanted to trend, you can do that as well to debug your ladder logic. And then really finally, I'm going to go over some of these motion axis commands, just so you can get an idea of how to start moving your axis for the first time. There's really 4 basic commands just to get started. So there's a MSO, which is motion servo on, MSF, motion servo off. Those turn the axis on and off. Motion axis jog will jog the axis, and then motion axis stop will stop the axis. But it'll remain running, but it won't be jogging anymore or moving anymore with the motion axis after a motion axis stop. So a motion servo on, or MSO, transitions the axis state from a stopped to a running state. So it's gonna release the motor brake, and the position is going to be held using the motor torque. So it will fight against you and try to retain its position. And just a little note here: your motion control tags for every instruction of this type need to be unique for all motion instructions. So just make a new tag for each motion instruction for the motion control tag. Motion servo off instruction transitions the axis state from running to stopped. This will set the servo holding brake. And so first make sure that the axis is not in motion before you do this. And again, the motion control tag needs to be a unique tag for all of these, each of these motion instructions in your project. So the motion axis jog command. So once you've MSO'd your axis and it's running, you can perform a motion axis jog command. And so this will command the axis to jog at a specific velocity. And I should mention, all of these motion instructions operate on a rising edge trigger. So the axis will continue to jog even if the rung transitions back to a low state. Like I'd already mentioned, the MAJ is sort of unique in that it will still operate even though you have a hardware overtravel fault in the opposite direction. So if you have a hardware overtravel positive fault, you can still jog in the negative direction. And for the input parameters for the motion axis jog instruction, you have you can specify a direction, a speed, speed units, and acceleration and deceleration rates, and jerk. which is the derivative of acceleration. For the motion axis stop instruction, what this does is it'll ramp your axis down to 0 speed. For example, if you're currently performing a jog. And then you're going to want to use this instruction sometime before you disable the axis with an MSF or with a safe torque off type of fault, so that the holding brakes will not set while the axis is in motion. So because the MAS instruction will ramp the axis down, electrically before you set those holding brakes. And that's really all I had for the presentation. Thank you for watching, and I'm going to pass it back to Rachel.
Thank you, Andrew. At this time, we don't have any active questions in the comment section, but we'll give just a couple of seconds here in case anyone has any questions as we come to a close. While we wait to see if there are follow-up questions, I just want to remind you that you can always reach out to us, and if you're watching this as a recording on the YouTube channel, please feel free to send your questions to macandmaclive@macandmac.com, that email address you see there on the screen. And with that, I will just like to thank Andrew for this presentation today and Steve for being our resource out in the comment section. Remember to subscribe to McNaughton-McKay YouTube channel for more industry content, and we look forward to seeing you live again soon. Thank you everyone for joining us today. Have a great day.